Good morning, everyone. Thank you for joining us in this webinar on using lookup tables in ladder logic. The presentation's roughly about 20 minutes. We'll go straight into it, and if you have any questions, we can get to those at the end.
Hello and welcome to today's webinar. Today we will be looking at using lookup tables in ladder logic. Let's look at our agenda for today. To begin, we will define what a lookup table is. We will then look at two applications for lookup tables. We will learn how to use lookup tables to retrieve values and to make calculations. We will also look at some useful ladder instructions for building a lookup table in logic. There will be demonstrations throughout, and we will finish with a Q&A session. Let's start by discussing what a lookup table is. Lookup tables can have different definitions depending on their application. When used for databases, a lookup table can be defined as a table that maps keys to values. For example, if we have a table with two columns, where the first column contains a list of keys and the second column contains a list of values, we could use the lookup table to find the bin location for a particular part number. In regards to computer science, a lookup table is an array that replaces a runtime computation with an array indexing operation. If we want to perform a calculation in our program, we could create a lookup table where the first column is the input to our computation and the second column is our output, instead of using a mathematical calculation. For example, to convert the resistance generated by an RTD temperature sensor to a temperature value, we could create a lookup table where the first column contains our measured resistance values and the second column contains the corresponding temperature values, instead of using a polynomial equation. We will look at both of these applications of lookup tables in our demonstrations today. Let's first look at the steps involved in implementing a database-style lookup table in ladder. First, we need to create a virtual table using multiple array variables. The first column in this table will be the first array, and the second column will be the second array. These will be aligned so that the data in the first array lines up with the results that are returned in the second array. In the example shown, the part numbers are shown in the first column, and the corresponding bin locations for each part number are shown in the second column. For database-style lookup tables, it is important that the first array does not contain any duplicate values. This is because when we look up a value in the first column, we want to make sure it is a unique value. Next, we will look at the logic required for this lookup table. We will be utilizing loops in our logic. We will use a loop to search the first column of our table for a value, such as a specific part number. When we have a match, we will make a note of the index, which is the value that we are incrementing. Indexes are always zero-based, meaning the first element in our array has an index of 0, the next element has an index of 1, and so on. In the example shown, we are looking for the fourth element of the array, which is 423. This has an index of 3. Once we have noted this index, we can use it to retrieve the corresponding value from the second array, which is the bin location with a value of 7. Now let's look at the key instructions we will be using for our lookup tables in ladder. Because we are utilizing loops, we will be using the label instruction, which marks the start of our loop. We will also be using the jump instruction, which allows us to jump to the different labels in our logic and will allow us to jump to the top of our loop. As we will be working through array data in a sequential fashion and retrieving data from arrays, we will also need to use the indirect move block. The indirect move block uses an index or a pointer to retrieve data in the array and move it to another variable. Now we will look at our first demonstration using a database-style lookup table in Cscape. Here we have our main loop, which has two subroutines. Our first subroutine, lookup location, will implement a database-style lookup table. For this demonstration, we have created a two-dimensional lookup table where the first column or the first array is going to be a list of barcodes. These are barcode values that we have scanned in and converted to an integer value. We have used constant move function blocks to load our lookup table. However, removable media function blocks, which retrieve a table of data from a removable memory card, such as a micro SD card, can also be used. If we select our constant move function block, we can look at it in more detail. Here we can see the first column in our lookup table, which contains a list of barcode values. These 10 values have been converted to integers and have been ordered sequentially. We will be retrieving these values from index 0 to 9. Now let's look at the second column of our lookup table, which contains the corresponding bin locations to these barcodes. These have also been placed in a constant move function block. Next, we will look at the logic we have implemented to look up a specific value from our lookup table. We will have a button on the touchscreen of our OCS that will look up our entered barcode value when pressed. Once we press our button, it will call our lookup location subroutine. The lookup table logic does not have to be in a subroutine, however, this allows us to isolate it from the rest of our logic. Let's look at this subroutine in more detail. We are using a loop in this demonstration to search through the entries in the first array one by one until we find a match. Before we start executing the loop, we first need to initialize our variables. We have set our index to 0, so the first value we will check in the array will have an index of 0. We have also set our location output, which will be the index or location of the value we are looking for if we find it. If we don't find this value, we need to return a value that is clearly invalid, so we will return a value of -1. Next, we have the label for the top of our loop, allowing us to jump to the top of our loop. As we go through the loop, we will retrieve values from the barcode list in our first array using the indirect move block, starting at index 0. Each time we go through the loop, it will increment indexes 0 through 9. These values will be copied into the variable value to test. If a value in our value to test variable is equal to the barcode value we are looking for, then we have found a match. If we find a match, we will then fall out of the loop. If we haven't found a match, we will increment our index, making sure we haven't exceeded the maximum value of the index. We will then jump to the beginning of the loop and then check the next index value. If we find a match and fall out of the loop, we will use this index value and retrieve the location data using the indirect move block. Now let's look at our bench setup for this demonstration. In the center of our OCS screen, we have our lookup table where the first array or first column contains our barcode values. Our second array or column then contains the corresponding location values for our barcodes. Let's demonstrate our program by searching for the barcode 23111. When we select the lookup button, our program returns a location value of 22. We can see that this is correct from the table on our screen. Now let's look for a barcode value that is not on the list. We will enter barcode 11111 and then press the lookup button again. This has returned a value of -1 for our location, which is an invalid value. Next, we will look at what is involved in building a lookup table for computational functions or math functions. As before, we first need to create a virtual table using multiple array variables. In the example shown, we have created a lookup table where the first column contains a list of measured resistances from a resistance thermometer. The second column contains the corresponding temperature values. The values in these arrays are aligned using a common index. For math-style lookup tables, it is important that the data in the first column is either in incremental, meaning low to high, or decremental, meaning high to low order. Once again, we will be utilizing loops in our logic for this lookup table. When using a lookup table for maths, you will usually not be able to find an exact match between the value you are checking and the value in the table. For example, if we are measuring a resistance value of 121.5 ohms, we will be looking for the first value in the table that is greater than this value. In our example shown, this is 123.242. We will then make a note of this index level, which in this case is an index of 6. In order to calculate the temperature based on the resistance recorded in this table as accurately as possible, we will retrieve 4 values. We will start with the value of the index we have noted, which was pointing at 123.242 on the resistance array. We will then create another index variable, which has an index of 1 less than this, and retrieve its value. We will also retrieve the corresponding temperatures for those two resistance values. These 4 values are highlighted in the example shown. We will retrieve these 4 values so we can perform a linear interpolation and calculate an accurate temperature based on the data in the table. We will take the minimum and maximum values for the input resistance and output temperature and plug them into the scale function block shown in the ladder screenshot. We will also plug in the resistance value we have measured, which is 121.5 in this example. Our scale function block will then give an accurate temperature value as an output, which in this case is 54.53. We know this output is accurate as it is in between our two temperature values, 50 and 60. There are some special cases that we need to take care of in our logic. For example, if the value we are trying to convert is not within the range of values in our table. In our example, this means if our measured resistance value is less than 100 or greater than 134.7. If this happens, we need to return an invalid value. In our logic, we will first check to see if the resistance value we want to convert is less than the first resistance value in the array. So if the value is less than 100, we will flag it. Another special case we have to look at is if the resistance value we are converting is exactly equal to the first entry in the resistance array. This is because when we do linear interpolation, we use the values of our current index and the index below that. So we are not able to use this method if there is no value before our current index. If this happens, we will have to drop out of our loop and report the first entry value in the second array. Let's look at our next demonstration in Cscape. This time we will be using a lookup table to perform a calculation. In this demonstration, we have a list of measured air temperatures which we want to use to calculate air density. Once again, we have created a two-dimensional lookup table with constant move blocks. The first column contains our temperature in degrees Celsius, ranging from 0 to 60. We can see that the entries in this column are not purely linear. They first go up in increments of 5 and then by 10. If we look at our second column, which has the corresponding air densities to these temperatures, we notice these values also are not linear. This would make it difficult to use a mathematical formula to perform our desired calculations, which is why we will be using a lookup table. Now let's look at our logic. Once again, we will have a button on our screen. When we press this button, it will call the subroutine that executes the lookup table for density. Let's look at this subroutine in detail. As before, we will first initialize our variables before we jump into the loop by setting our index to 0, so we start at the top of our initial array. We have also set our air density output to an invalid value with the value of -1. If the temperature value that we are looking for is not within the range in our lookup table, our program will return this invalid value. Next, we have the start of our loop. We will start by retrieving the first temperature value that we want to compare our value against. We have the air temperature value we have measured, which we will be comparing against the first temperature value in our array. We are comparing these values to make sure our measured temperature value aligns with the two special cases we looked at earlier, the first time we go through our loop. The first value that will go through our loop will have an index of 0. So if the air temperature that we are measuring is less than the first value in the temperature table, we will flag this and drop out of the loop. We also want to check when the index is 0, assuming it is not below 0, whether the air temperature value we have measured is exactly equal to the first entry in the temperature array or not. If it is equal, we will not be able to use the linear interpolation method, so we will flag this and drop out of the loop. We will then report the air density as the first entry in our air density array. Assuming our value falls within the range of air temperatures in our table, then our main code will be executed. Provided neither of these two conditions are met, we will check if our air temperature is less than the temperature we are testing against. If it is less than this, then we have found the point in the table where we are able to do our linear interpolation, as we need values above and below the value that we're testing. When this happens, we will set a bit that shows that we have found a value that is less than our measured air temperature. If neither of our special cases have been met, and we have not found our entry, then we will increment our index and we will return to the top of our loop. Once we fall out of the loop, if we have found the entry we are looking for, we are able to do linear interpolation. To do this, we create two indexes, one which is the location of the entry we were looking for, and then we create a new index for the index one less than this. Using these two indexes, we use indirect moves to retrieve the high and low temperatures from the first column of our table, which are the temperatures above and below the temperature we are checking against. We will also retrieve the two corresponding density values to both of these temperatures. Using these values we have retrieved using indirect moves, we will execute our scale function block and calculate our air density. In our special case, where the first entry of our array matches our temperature exactly, we will perform a simple move command to move the first value in the density array as our air density. In the case where our value is below the first value in the array, we will be returned our invalid value of -1. Now let's look at our bench setup for this demonstration. On our screen, we have our two-dimensional lookup table with air temperature in the first column or the first array, and air density in the second column or the second array. First, we will test our program by setting the temperature as 0. According to our table, this should return an air density value of 1.292. This proves to us that our special case was handled properly. Now let's try setting the value as 22.5 degrees Celsius. If we look at our temperature table, we can see that 22.5 degrees Celsius is between 20 and 25. Using linear interpolation, we know that the return value should be midway between 1.204 and 1.18, which we get here. Finally, we will set our air temperature as 50 degrees Celsius. We can see that the returned value we get matches the corresponding air density to 50 degrees Celsius in the lookup table. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, so we are back on in 2 weeks with setting the default IO state. And after that, we will be going back to weekly webinars every Thursday again. I'll just give a quick check of the questions panel. There doesn't seem to be anything in on that. It's kind of a nice straightforward one. Okay, other than that, thank you all for joining us this morning, and we'll see you next time.